Hi, this is Ms. Fitzmaurice, and this video is an explanation of the problem on page 20 of your Unit 5 packet. So what I want you to do before you finish watching this video is, first of all, if you have not figured out the problem, I want you to go through and annotate the problem. I want you to decide which concept you can use for A, B, and C, and then go ahead, try to solve the problems, watch the solution. Alright, so it says we have this situation. It says a swing seat of mass M is connected to a fixed point P by a massless cord L. A child also of mass M sits on the seat and begins to swing with zero velocity at the position at which the cord makes a 60-degree angle. Okay, the swing continues down until the cord is exactly vertical. At that point, the kid jumps off the swing, and they jump straight in the horizontal direction. The swing then continues in the same direction until its cord makes a 45-degree angle with the vertical as shown in figure 2. Okay, so in part A, it says determine the speed of the child in the seat just at the lowest point. Okay, so we want to know what is the velocity right here. Okay, to do this, we know gravitational potential energy here. We can figure out gravitational potential energy right here, and so we can use conservation of energy. So for part A, we're going to use conservation of energy. Sigma naught equals sigma E. We know at the beginning, the child and the swing only have gravitational energy, and at the end, they only have kinetic. For part B, it asks us to determine the speed if the seat it says if, but it means of, immediately after the child dismounts. Okay, so this is kind of weird to think about, but the most useful concept right here is going to be conservation of energy, because we have at this moment, okay, when the kid is still on the swing, we have a velocity. Okay, that's our before. Imagine the kid is still right here on the swing. Afterwards, the swing is moving up and the kid is moving to the side. So we're actually going to be able to use conservation of momentum. Importantly, conservation of momentum only in the x direction, because there are no total outside x forces. There is a total outside y force, and that would be our tension minus Fg, which gives us our centripetal velocity. Finally, in C, it asks us to determine of the speed of the child immediately after he dismounts from the swing. Okay, so I'm going to back up for 1 second. I'm going to say, oh, I guess we don't know enough to use conservation of momentum right there. We can use conservation of energy because our swing goes up to 45 degrees. So we're going to use conservation of energy in part B and conservation of momentum in part C. Sorry for the confusion. Okay, so in part A, again, we're using conservation of energy. Sigma E naught equals sigma E. And we know that at the beginning we have only gravitational potential energy, and at the end we only have kinetic energy. We want to know the speed. So we have mgh equals 1/2 mv squared. The hard part is figuring out what h is going to be. Okay, and so just like we did in a previous problem, we have a string with a certain length, right? And we want to know the difference between how high the thing is when it's extended and then how high it is when it's all the way to the ground. So we have a height equals 0 right here, and we know this whole length is 0, or is L. So this length right here must be L minus cosine 60, because this length right here will be L cosine 60. And hopefully you remember that cosine 60 is 1/2, so that's going to be L over 2. Okay, so we have this green part is our whole length L minus L over 2, which ends up being L over 2. Now we can go ahead and plug that in for our height. We have mg L over 2 is equal to 1/2 mv squared. Okay, we get rid of our m's, and we can also actually get rid of our factors of 1/2, and we have v squared equals gl, or v is equal to the square root of gl. Okay, so now the kid jumps off and the swing only makes it up to 45 degrees. Okay, and so again, we're going to use this strategy to find heights. So we're going to say h equals 0 here, and over here, h is going to be equal to, again, our whole length L minus whatever this part is. Okay, this part will be L cosine 45, and so we have h is equal to L minus L cosine 45. I'm going to factor out my L. I have h is equal to L times 1 minus cosine 45, but the cosine of 45 is just 1 over root 2. Okay, so we can once again go ahead and solve using conservation of energy. Sigma E naught equals sigma E. Okay, so the swing by itself, that's the energy at the beginning. It has only kinetic energy, 1/2 mv squared, and at the end it has only gravitational potential energy. Now these m's go away, and the height we're going to replace, remember, with L times 1 minus 1 over root 2. So we have 1/2 v squared is equal to g times L times 1 minus 1 over root 2. Okay, we can find a number for this, and it's about 0.292. Okay. To get rid of our factor of 1/2, we multiply that by 2, and so v squared is equal to g times L times 0.585. Okay, to find v, we take the square root, and we find that v is equal to about 0.76 times the square root of g times L. Alright, so in C, because the child is jumping off of the swing, we can use a collision or conservation of momentum to solve this problem. So our before picture, our person is on the swing and they're going with the speed. We know that speed is equal to the square root of GL. Okay, so that's our initial picture. Afterwards, the kid is going off with some initial speed, we don't know what, and the swing has a speed of v swing final is equal to 0.76 times square root of GL, 0.76 square root of GL. Okay, so we're going to use conservation of momentum. We have sigma p naught equals sigma p at the beginning. Our person and our swing are moving together. Combined, they have a mass of 2m, and we're going to multiply that by their velocity, GL. At the end, we have the swing's momentum, so m swing, v swing, plus m child, v child. Okay, so we have 2m square root of GL is equal to the mass of the swing is just m times 0.76 square root of GL plus m VC, and we're solving, remember, for this VC. Hopefully you noticed that we have an m in every term, so if I divide both sides by m's, they just go away. And now I can solve for VC. I end up with VC is equal to the square root of GL times 2 minus 0.76, which is 1.24 times the square root of GL.